Welcome back, everyone, to our deep dive into the OEIS, the online encyclopedia of integer sequences.
It's great to be back.
Today, we're going to be looking at a sequence that takes us right to the heart of graph theory.
Yeah, a 000088.
Is 000088.
Exactly.
This sequence dives into the world of simple graphs. No loops, no multiple edges between the same nodes, just the building blocks.
The foundations.
Yeah. By the end of this deep dive, you'll grasp how this sequence works, why it matters in different fields, and honestly, just get a taste of the really cool mathematical landscape it inhabits.
Sounds fun.
So the first few terms of A000088, 1, 1, 2, 4, 11, 34.
Yeah, and these numbers represent the number of simple graphs you can make as you add more and more nodes.
It's like all the different ways you can connect dots.
Exactly, like picture connecting dots, and as you add more dots, the ways to connect them just explode. That's what this sequence is all about.
So it's not just about the numbers themselves, it's about the patterns they reveal.
Right, and one key pattern is the asymptotic behavior of the sequence. These numbers, they grow really fast, almost as fast as 2 to the power of n squared.
So the more nodes you add, the more complex the possibilities become.
Exponentially more complex.
Okay, but how do we actually get these numbers? What's the math behind this sequence?
Well, there are a few key formulas. Some are pretty straightforward, others not so much.
Give us a taste.
For instance, one formula uses factorials, another involves binomial coefficients. We're talking about some serious mathematical machinery here.
Okay, so it's more than just drawing dots and counting lines.
Oh, definitely. This is where it gets really elegant.
So A00000088, it's not just some lone wolf sequence, is it?
No, not at all. It's connected to a whole network of other sequences in the OEIS.
Like a family tree?
More like a web, an interconnected web of mathematical relationships.
So give us an example.
Sure. Take A001349. This sequence counts connected simple graphs, where every node has a path to every other node. You can actually get from A000088 to A001349 using a mathematical operation called the Euler transform.
The Euler transform. Okay, so we're talking about these deep connections between different types of graphs.
Precisely. It highlights how these seemingly different concepts are actually related in this elegant mathematical dance.
Okay, but our source material also mentions this connection to something called sign patterns of matrices. What is that about? That sounds pretty different from counting graphs.
You're right, it does. It might seem like we've jumped to a whole different area of math, but that's the beauty of it all. It turns out the same sequence, A000008, can also be used to count something called equivalence classes of sign patterns in certain types of matrices.
So these totally different concepts, graphs and matrices, are somehow linked by the same underlying sequence.
Yes. And that's not all. This just scratches the surface of how A000008 connects to other areas of math. There's so much more to explore.
It's amazing how this sequence that started with just counting simple graphs has led us to this. It really speaks to the interconnectedness of math, doesn't it?
It really does. And it raises an important question. Why should anyone, especially those of us in STEM fields, care about this seemingly abstract sequence?
That is a great question. Why should we care? We'll explore that in just a moment, so stay with us. I mean, it's cool to see all the math, but where does A000000 actually come up in real life?
Well, one really important application is in social network analysis.
Social networks.
Yeah, you can represent them as graphs. People are the nodes, and their relationships are the edges.
Makes sense.
So A000088, by counting all the possible simple graphs, it gives us a way to understand how these social networks could be structured, like the underlying framework.
So, if we understand the properties of those simple graphs, we can get insights into how information spreads, how communities form.
Yeah, even how marketing campaigns might be designed for maximum impact. All sorts of things.
It's like a blueprint for social dynamics.
In a way, yeah. And it goes beyond just social stuff. In chemistry, molecules can be modeled as graphs, too.
Oh, right. Atoms as nodes and bonds as edges.
Exactly.
So ED000088 can help us understand the huge number of potential molecular structures.
That's the idea. It has big implications for things like drug discovery and material science.
Yeah, if you can analyze all the different ways atoms can connect you, you could maybe discover new molecules with specific properties.
Exactly. New medicines, materials, it even helps us understand chemical reactions at a deeper level.
Wow, that's incredible. So it's like a blueprint for the molecular world, too.
It's a powerful tool.
I've also heard this sequence pops up in physics.
It does.
How so?
For example, in statistical mechanics, physicists use graphs to model model like the interactions between particles.
Oh,
So ED000088 becomes important when they're analyzing the different configurations these systems can have, which is key for understanding things like entropy and phase transitions.
so it's helping physicists wrestle with some of the most fundamental ideas in the universe.
It is. It really is.
And all from just counting simple graphs.
It's remarkable, isn't it?
It really is.
Yeah.
And what about computer science? I know graph theory is big there.
Oh, huge. Graph theory is everywhere in computer science.
Yeah.
It's essential for designing efficient algorithms and data structures.
Right.
Understanding how many simple graphs there are and what their properties are, that's key for things like network routing, data mining, or even machine learning.
I mean, it's everywhere we look, this 80000088, just woven into the fabric of so many different fields.
Yeah, and it's a great example of how interconnected math is and how powerful it can be for unlocking insights in all sorts of different areas of science and technology. But this also brings up a question.
What's that?
Well, we've talked about how fast the number of simple graphs grows, right? Like
Yeah.
exponentially. So is there a point where it becomes impossible to study them all? Like even with supercomputers, is there a limit to what we can handle?
That's a really interesting question.
Right, because with that exponential growth,
Yeah.
it seems like there's got to be a limit.
Like a computational ceiling.
Yeah,
Yeah.
exactly.
So you're saying there could be all these, like, undiscovered graph structures out there
Potentially, yeah.
just because we can't compute them.
It's kind of humbling.
It is, yeah.
It makes you realize the limitations.
Even with all our technology,
Exactly.
there are still boundaries.
To what we can know.
But that also makes it even more exciting, right?
I think so.
The pursuit of knowledge.
Like sense of the unknown.
There's always more to discover.
Absolutely. And the OEIS
Yeah.
with all its sequences.
It gives us a way to
Those
explore.
uncharted territories.
It reminds us that math is never finished.
Well said for me. I think we've given everyone a lot to think about today. I hope so. Yeah. Starting with O as 00000088.
It's counting simple graphs.
We've seen how it connects to so many different areas.
From social networks to molecules to the cosmos.
Yeah, and we even touched on the limits of our knowledge.
The computational challenges.
But it's that constant striving.
To push those boundaries.
That's what makes it so fascinating.
So thanks for joining us on this deep dive into A000088.
It's been a pleasure.
We hope you've gained a new appreciation for the power of integer sequences.
And how they connect everything.
From math to science to technology.
And beyond.
Until next time.